7. So anytime you're graphing an exponential function, 2 to the x and 3 to the x are growth functions. They're going to kind of look like this. They're growing. That's a growth function. Population growth. Hopefully your money grows exponentially. There's 3 key points that I like to look at every single time I'm graphing an exponential function. I want to see what is the graph doing at -1, 0, and +1 for x. -1, 0, and +1 for x. And if you can just make a table for yourself, then it doesn't matter what base. They might throw at you 7 to the x. They might throw at you 9 to the x, 3 to the x. So I can change the base, but the process stays the same. If the base gets raised to the negative first power, what happens to the base? It's just the reciprocal of the base, not the negative of the base, right? 2 to the negative first power is 1/2. What's 3 to the negative first power? 1/3. So the first key point is the reciprocal of the base, either 1/2 in this case or 1/3 in this case. What's anything to the 0 power? So no matter what I raise to the 0 power, my y-intercept will always be a 1. Anything to the 0 power is 1. And then what happens when I raise the base to the first power? 2 to the first, 3 to the first, 8 to the first. I get the base back, right? Anything to the first power is itself. So in this problem, I would get 2 back. And in this problem, I would get 3 back. And if it was the 7th, I would get 7 back. So if you can just kind of remember that that pattern holds for any exponential function, it's the reciprocal of the base. Anything to the 0 power is 1, and then it's the base itself. You can graph any exponential function. They're always going to look like this. So at -1, I'm at 1/2. At 0, I'm at 1. And at 1, I'm at 2 on this graph. So those are my 3 key points. And then on the other function, it looks almost the same. I'm at 1/3, then I'm at 1, and then I'm up here at 3. So it's a little bit steeper, but it looks almost identical. And think about it, if it was 10 to the x, it would be a lot steeper, right? Oh. So 10 to the x would go like this, straight up, right? This is a little bit more gradual. There's one more important feature on these graphs, and it's called an asymptote. And I think this is the first time you've seen an asymptote. So an asymptote is a dotted line. In this case, it's right at y equals 0. Your graph gets smaller and smaller and smaller, but it can never go below that dotted line. Because this is just going to be a fraction, right? 1/4, 1/8, 1/16, 1/1000. It's going to be very small, but it can never get to that 0. It's going to be 1 over something. Those are growth functions. Guess what? The other 2 are called decay functions, and they're just going in the opposite direction because you're starting out with a fraction. So when you start out with a fraction and we do those same key points, it just ends up going in the opposite direction. What happens when I take the base to the negative first power? What does a negative exponent do? Takes a reciprocal. So when I start with a fraction, I get the number 2 in this box now. So it's flip-flopping the order of your points. So the negative first power is 2, and on this one, the negative first power is 3. What's anything to the 0 power? So even if it's a fraction, anything to the 0 power is still 1. So our y-intercept is always at 1. And then what happens when I raise to the first power? I get itself back, right? So 2 to the first was 2. 1/2 to the first is just the number 1/2. So this guy gets to be 1/2, and this one gets to be 1/3 because it's the base back again. When you graph those points, you'll see that it's just graphs from up top flipped over the y-axis. Because at -1, I'm get 2, 1, and then 1/2. So I'm coming down. I'm a decay function. This one would be 3, 1, and 1/3. So I'm a decay function. See how it's almost the same set of points, but it's the same process. Plug in -1, plug in 0, plug in 1, and that gives you your exponential curve. And then these also have an asymptote in the same location, y equals 0. So once you've done, 4 of these graphs, I could throw at you a base of 1/5 or a base of 6. And it's the same process. It's always going to have the base in your set of points. So the next page is just a summary of all of those facts that we basically just talked about for 2 to the x or 1/2 to the x. What would be their domain, range, y-intercept, asymptote? So you tell me, you look at the next page, what would be the domain for these functions? Can I go this way forever? Yes, right? I'm going this way forever. Can I go this way forever? Can't go down here, can I, for y? So y has to be what? Above 0. So for every exponential function, they have the same domain and range. So I want you to write all real numbers, but y is greater than 0 for both of these. Because it doesn't matter if it's a fraction or if it's a non-fraction. What was the y-intercept on both graphs? The y-intercept is always where? Always 0, 1. Now if this was growth, right? Growth is increasing, so the other one is decreasing, decay. So that's the only difference. These graphs were increasing, like your money, and these graphs were decreasing. So something that might decrease over time is like the value of your car. Exponentially, it is worth less over time. And then we said y equals 0 is the horizontal asymptote. Has anyone ever heard of the word discrete before? We're going to learn about it this year, but we haven't learned about it yet. Discrete means dots that you don't connect. Continuous means you can connect the dots. So we have continuous graphs, but we're going to learn about, other times where you might not have a continuous graph. So this one was going up and this one was going down. So at least you'll have the facts in your notes. This says, does anything change if we change the base? So would the domain or range or y-intercept change if the base was 4 to the x or 100 to the x? No, it just changes the steepness of the graph. So it changes the steepness, how steep the growth graph is or how not steep it is. So let's think about what would the points be if you had 1/4. See if you can come up with what your points would be. And then same thing, what if you had 10 to the x? Before you graph it, let's make sure the table of values are correct. So baby, see if you can do it for yourself what the table would be. If you plugged in -1, if you plugged in 0, if you plugged in 1. Before you graph it, let's just check that our values are correct. All right, so there's the graphs for 1/4 and 10. So the last thing, and I told you you'd have a couple minutes to decorate, right? I want you to copy the transformation rules because we've done these with exponential functions. So you should already know the transformation rules for up, down, right, or left. But it looks different when it's written as an exponential function than as a quadratic. So I wanted you to have this as a resource because if you know the parent function, you should be able to grab a transformation, like shift everything right 5. So here's up or down, and this is what right and left would look like. Those are with x in the exponent, and these are outside the function. So up, down, right, and left. So we're going to practice the transformation rules again from unit 1 and 2, or actually unit 2, I think, with quadratic transformations. I'll give you 10 more seconds to copy those, and I'm sliding it down to the other transformation rules. Flip it upside down or flip it over the y-axis. Make it steeper or make it less steep. The base stays the same, but you can multiply it, make it steeper or less steep out here. The A is your steepness and the B is called your base. So the base is not a transformation rule. The A is a stretch. All right, you're going to help me